I'll take that as a yes. Cool. Okay, we'll start. So. Okay, so yeah, that works. Y'all get to hear me projected now. Thanks, Evan. You're really useful. Jesus Christ. Y'all don't need to hear this. Or y'all don't need the mic on, but with that said, I'll try to use this anyway. This is stupid. Anyway, so step one is today's meeting is on performance metrics. So basically, we're going to be measuring we're going to be learning how you can measure how good a model is. Now, first things first. Quick note on the final project. As I said, the project is going to be going over. You'll get tabular data. Some will explain everything next meeting, but the skinny is you're taking tabular data and you're trying to predict whether someone is hard to see based on that. Now, I will be putting a silent link into the Pioneers channel of the Discord momentarily. Momentarily, as in how quickly I can copy paste something. But once I put that in there, I'm going to give you guys like 5 minutes to go and sign yourselves up. Make sure that first off, if you have any teams that you want to work in, your teams can only be up to 3 people. If you want to work solo, that's great. Don't really care. Up to you. It's your own ass at the end of the day. So you do that. But in general, I will be sending out I'll be sending over everything. We'll be sending that link out right now. Teams of 3. And yeah, so in 3, 2, 1, it's in the Discord. Check the Pioneer, now put it in general. Cool. Check general. Don't listen to me. And again, sign up for that quickly, and y'all should be good. Do you not have the ability to edit? Are you guys using your terminals?
No, I have the ability to edit.
Okay, so if you have the ability to edit, that means you're on your terminal, which is good. If you do not have the ability to edit, that means you're not on your terminal account, which case please sign into your terminal account. If you do not have the ability to edit and you are on your terminal account, there is a big problem, and I don't know if I haven't paid enough to do that. So yeah. So yeah, sign in with your terminal if you're having issues and try. If that doesn't work. Oh no. Don't look at the slides. I'll give you till like 5:12. What, sorry?
It doesn't work with the terminal.
Oh, Jesus Christ, thank you, Google, for never working properly. It seems, no, Jesus. Yeah, both of you get to request access and I think it's on. Yeah, I don't. That's extraordinarily weird. But you know what? How about this? In the meantime, I'll just throw your names in there because obviously I can do that. So team 0 example, cool, my guy. Thank you, Samrat, for throwing my Discord in there. That's really helpful. You guys should all have it anyway. But yeah, first things first. So guy on the left with the Apple computer. What's your name?
Austin.
Austin. Do you want to work individually or just on the team?
I'll work individually.
Okay, cool. Austin. What's your last initial?
S.
S. And do you know your Discord just off the top of your head?
I know.
All right, cool. Well, once you get access, we'll deal with that. I will let some right now. Next up, your name. Keshav. Is it Keshav?
Yep.
Okay, cool. Keshav, last initial? G. Cool. Do you know your Discord off the top of your head? What's the reason?
Keshav.
So it's just Keshav?
Yeah.
Keshav 6317. Cool. Ready then. Okay. So, Austin, can you check your Discord quick?
This is Austin.
Oh, is it just Austin? Do you know the numbers?
Yeah, 1627.
So it's just Austin, numbers 1627. All right, cool. Keshav, Austin, I put you up on the same team. Sorry if you don't want that. But, while I have the ability to play matchmaker, I will play matchmaker. So yeah. With that said, both of you please at Samrat in the Discord and tell him that you do not have access to it. So you'll be able to sort that.
Yeah, same here.
All right, lovely. You also have time. What's your name?
Jimmy.
Jimmy? Jimmy, do you have any preference on like what team you're on or?
Yeah, so I will, he's not moving right now, but, his name is Liquid, MUKUND.
Okay, cool. So Jimmy, I'll add your name first. Jimmy, last initial.
T.
T, Discord.
LEJIX.
LEJIX, numbers.
4108.
4108. Okay, and Mukund, do you know his last initial?
S.
All right, lovely. Discord, do you know it?
Maybe just his name and number 8165.
Okay, 8165. Lovely, cool. Well, I put you guys on team 5, so you guys have fun with that. You guys still have fun?
I also can't have it.
What the hell is? Okay, someone's getting fired. Can everyone except YouTube not access it?
Were any of you guys here last semester? No, we did it last semester. Yeah.
All right, so whoever we put in charge of it this semester apparently needs to get their pay cut down from 0 to -0, I guess. All right, how about this? Because I'm not gonna enter everyone manually, and I'm also not. That's not laptop, sorry. How about this? All of you, like right now, just like individually at Samrat in general, and just be like, I cannot access the sign-up document, and just say that like 30 times. No, well, it does say 30 times, but like each of you say that once, so that Samrat can get the thing. He said he couldn't make the meeting, but like this is clearly an issue, and I don't need to be able to do that. So yeah, add him and tell him something broken. I'll also do that as well. Also, Samrat Python lead for those who did not realize it. Right, yeah. So yeah, for those of you who I did just enter your name, when you get access, just make sure everything looks good. For those of you who I have not dealt with, you know, I will keep you updated as for when Samrat says. In the meantime, yeah, that didn't go as well as I wanted to, but you know, we'll deal with that when we get to it. So yeah, hopefully Samrat replies soon. In the meantime, let's shift on from that for a second. Also, for those in the Zoom meeting who like just joined, it's in general, it's in general. It's the Excel link I put in general. If you guys don't have access, then don't bother. But if you do have access, well, that works. So anyway, first things first. When discussing performance metrics, it's important to understand, you know, how do we want our models to look? Now, I know this sounds kind of like a really open-ended question, but I'm going to pose it to you anyway, because, you know, I have the teaching abilities of second grade. So yeah, if you guys are thinking about a model, if someone asks you a question of like, you know, how should this model work? What was your like instinctual response to? Okay, so congrats, go to the business school, thank you. Something beyond just saying AI, because yeah, we're not business. Yep, what's up?
You like as efficient as possible.
Okay, as efficient as possible. Cool. Yep.
I mean, in all seriousness, you could like actually say what algorithm you're using, like are you using your neighbor's software algorithm? Just be a bit more specific.
Okay, so one of you said, you know, be efficient. One of you said, tell them what the algorithm is. Any other takers? Yep.
You show that it's like improving.
Showing that it's improving. Okay. Yep.
Small amounts of error.
Small amounts of error.
Are you just asking how much?
Well, I mean, I've got a point to this, but you know, you can answer.
Give you an output.
Should give you an output. I guess. No, I mean, like, I guess I would joke that type error is technically an output, but it's not the output. But you know, anyway, all right, cool. Well, none of you got what I was getting for, but that's fine because that's why we're here. So when I ask how should the model work, a lot of people think, you know, the first question is, okay, well, how should it work in terms of like, you know, you want it to be efficient, you want it to, you know, what's the algorithm, stuff like that. In reality, I guess how to be efficient does kind of come close, but the whole idea with how should a model work is basically, in terms of its outputs, what are the distribution of its outputs? So, for example, right, say I'm making a model, right, say I have two different, something like stat for 20, that's all it pulls up, but like, let's say I have two different processes for modeling a coin flip, right? One of them is based on some weird mess of a black box, but we know that 51% of the time it outputs heads, and 49% of the time it outputs tails, right? And then there's another process that 99% of the time it outputs heads, 1% of the time it outputs tails, right? Now, which of those models would perform better for modeling a coin flip? Which one? First one or second one? First one, right? Yeah, obviously. Coin flips are ideally 50-50, so you want it as close to 50-50 as possible. And the one that's 99-1 is in no way near a coin flip, right? That is essentially what I'm trying to get at. When we ask how should a model work, the idea is mainly, how does, what is the distribution of its outputs? If you have a process, or if you think of the model as like a random, statistically called a random variable, but if you just think of it as just like a process that like you throw something in and randomly you get something out, right? Based on just throwing a bunch of inputs into it, what is the distribution of the outputs, right? So let's take something like a random number generator, right? Random number generators have an input, it's a random seed, don't worry about all that. But basically, a random number generator, let's say it's supposed to generate a number that's 1, 2, 3, 4, 5, 6, right? You want that, it needs to generate each number 1/6 of the time. So in 60 inputs, if you run it 60 times, it should have something about like, 10 times per number, right? Assuming your uniform distribution. Now, reality, random number generators are a lot more complex. That's all besides the point. Ideally, if it has a 1/6 chance of choosing something, then you want it to have probability 1/6. So the outputs, if you have 60 outputs, 10 of them should be like, number 1, 10 of them should be 2, so on and so forth, right? Now, if you have another model, right? Say you have a model that's like, let's think about a model that's trying to identify if someone has cancer, right? And well, I don't necessarily know, okay, I'm not going to choose cancer because that's not something I'm not expert, that's not something I know. But let's say that we choose something that's trying to figure out whether or not someone's Lyme, right? Lyme disease, for those who don't know, is a skin lesion that, wow, that gets really loud when I look at the mic. It's a skin lesion, right? And notably, skin lesions will exhibit themselves semi-differently in different colored people because, darker skin, lighter skin, it's obviously a discoloration, and most people would look at it and be like, yeah, there's something wrong. But if you look at a model, depending on what the training set is, it may not be able to do, right? Now, whatever the distribution of the outputs are, so basically, whatever it is, we're classifying whether or not a certain skin color is healthy or unhealthy. That should be almost equivalent across, every possible skin color, right? So it should treat white people the same as brown people, the same as, other different skin colors, right? And the reason for that is, it's pretty obvious all of the races. But generally, that's kind of a good rule of thumb to follow, right? But the thing is, you don't want it to, look at white skin and think that's normal, and healthy white skin and think, okay, that's normal, and then look at a black person with the same color with healthy skin and think, oh, the skin's a different color, there's a problem here. Yeah, that's not good, right? So when we ask how should a model work, the main question, or the question we're really asking again today is, or at least for this, is entirely what do we want the outputs to look like? How does it perform based on a certain group of examples, right? So that whole idea of how it works, how well it works on a certain group of examples or whatever, that's what we call the model's performance, right? Now there's a variety of different ways to define performance. As I've said right there, it's entirely tested, right? So let's think. So for example, again, if I'm modeling a coin flip, right? I'm not really measuring I'm not measuring necessarily there's no real concept of accuracy, right? It's not number of correct outcomes out of number of tokens, right? Because what's a correct outcome for a coin flip? It's not a correct outcome, right? But what you're doing is you need to run it on a bunch of different examples, and then you need to go, okay, so then we show that the probability of heads and the probability of tails are both at least 50%, right? Or close enough to 50% that it's good enough. In the same way, let's say that I'm trying to get a let's say that I'm trying to get some sort of let's use cancer this time. Let's say that I'm trying to diagnose someone with cancer, right? Ideally, you don't want the model to be classifying. Well, it's what we call false positive, right? If you don't have cancer, you don't want the model to be saying that someone has cancer, right? And moreover, and this is a bigger problem, especially with medicine, you don't want to have someone with cancer and then the model says that they don't have cancer. That's a false negative. That is really, really, really bad. A false positive is bad because of like insurance costs and stuff, and obviously like stress and hardship. Right? But a false negative is really bad because you basically just let someone to die depending on how bad the cancer is. And I don't think there's any cancer that is good, but you know what I mean. You're basically just leaving someone to die, right? That is very not good. That's very bad. Sorry. And so that's the whole idea of, you know, for the task, right? Depending on what you are doing, certain measures of performance or certain certain measures of performance that you have may be more desirable to look at than others. And moreover, like, you know, how big they are, like the size of them may actually depend. So for example, in terms of like a classification, that's what I mean in the second bullet point. How many of you have taken CMS 351 other than so on? I know that we can not have the same class. None of you? Okay. How many of you are CS majors? Alrighty, cool. For all of you CS majors, you will have to take a class called CMS 351. CMS 351 is an introduction to algorithms. I think now it's taught by Justin, so my advice may be out of date. But at the time, it was taught by a professor named Clyde Kruskal. Clyde Kruskal, for those of you who know what Kruskal's algorithm is, yeah, the guy who found Kruskal's algorithm was Clyde Kruskal's grandfather. So he is a very smart man. He's also the worst professor at UMD, probably. It's bad. I don't know. I don't want to like slag him off too much with the technical meaning of that. Really shouldn't do it, but like, yeah, right. It's disorganized. It's name. Yeah, do that. Basically, and you can take this from Soham and I who had friends who took Russell. If you got 65% overall in this class, that was an A. That's how hard it was. I think it was 65, 70 was in. If you got like a 45%, I'm pretty sure that was around a C or enough to pass. It's a hard class, right? Those of you who may be like, you know, bio-y or whatever, and have dealt with the chem department, same sort of stuff. Those of you that have had like, you know, certain math classes, I know one of my math classes had, like in math 410 had a 20% curve, I got an 84 curve up to May. So, you know, stuff like that. You know, different levels of performance. So like, especially with classical, right? If I said I have a 65% of English 101, I think I'd probably not, that would not be good. I'd have to retake a lot of courses. If I had a 65% CMS 351, well, I could just sleep because that's amazing, right? That basically means you did really well. And so that relates to other things. So for example, let's say that relates to models. So like if you have a machine learning model, let's say that it has a 99% accuracy, right? For those of you who remember last time, I talked about how you can have like really biased training sets, right? So say that I have, you know, like not 100 different samples, 99 from class 0 and 1 from class 1, right? And I have a model that's basically just predicting 0 every time. I mean, if I run it on that set, I get well, if I ran it on that, I get like 99% accuracy. And that would look really good because like, oh my god, it's 99%. In reality, it just predicts 0 every time, so it's wrong, you know, anytime you feed it a 1. So if you had a balanced training set, the testing set, it would be about 50% accuracy, right? Because you got 50 plus 0, 50 plus 1. Or if you have a balanced testing set, and you feed it to that, it would get an accuracy of about 50, right? So in certain ways, you have to know what the task is. You have to know what the distribution of your data is. And you need to have different performance metrics so that you're able to figure things out. So stuff like accuracy is always a punching bag, by the way. If you ever look up how machine learning performance is measured, they always shit on accuracy. It's good in certain scenarios, but you need to know what the scenarios are. But in general, there are multiple different metrics for this exact reason. We don't just measure things always using one, like, you know, for one great metric, because depending on what your task is, what your problem is, what the data set looks like in general, you need to have different performance metrics so that you'll be able to show that your model is actually good based on certain metrics. Now, the issues we'll see later, and I'll be talking about them individually. For the purpose of this lecture, by the way, we'll be talking about 3 different metrics: accuracy, ANC, which is area under curve, and the confusion matrix. This is not comprehensive. As I said, there is a million. There's actually more than a million. Statistics people love to just take their time to look at performance metrics, and we love them for it, but statistics. But in general, some don't need to just. Yeah, but in general, there are multiple different ways of measuring performance, and it is, I mean, it's a large thing. Like depending on the task, especially in research, people will create their own performance metrics, right? They'll be like, oh, this score that's derived from this, this, and this is what we're using to measure a model. And it seems weird, right? Because it's like, oh, I'm just pulling something out of thin air and it makes me look good, right? But in reality, what it is just, okay, this is the best, in the researcher's mind, this is the best measure of indicating that this model that I made is actually useful, or it's good in this way, right? So, as I said, it's not comprehensive at all. Please read it on your own time if you want to work in AI in the future, especially if you want to do research, because knowing all of that stuff, knowing, having some familiarity with these, you know, a large variety of performance metrics, that's something, because it helps you understand which papers have like actually decent models. It also helps you understand why when your boss tells you to use this random formative index, you feel like, oh yeah, I guess that kind of makes sense. And yeah, but anyway, moving on. The first metric we're talking about today is accuracy. Accuracy is extraordinarily simple. Do I need to elaborate more? All right, cool, cheers. We'll move on to the slide because I will talk about practice. But accuracy, as I just mentioned, it has pros and cons. Now, pros are well known and easy to interpret, right? Since you have been children, you have been taking tests, and you know how well you do on a test. Your score is basically a measure of your accuracy on how good you are at whatever. And the material on that test, not a communication test. But in general, right? That's just accuracy. You see the number of questions asked, you see the number of correct answers. Got like 0.85 out of 100. Cool, I know what that means, right? And it's just simple like that. However, as I said, it is terrible for unbalanced data. Again, if you have 99 of something and 1 of the other thing, and you get 99% accuracy by only predicting that first class, that's not good. That means your model's got a problem, but you won't know it if you just look at accuracy. And yeah, as I said, it requires homogeneous data set. When I say homogeneous, I just mean you need to have like a balance data set. So if you have 9 different classes, you need to have semi-equal amounts of all 9. Otherwise, just looking at the accuracy score is a very, very misleading. So yeah, that's accuracy. Now, first one that should be you guys, unless you know this already, or took this last semester, which is notice and maybe not read the PowerPoint. We have AUC or rough AUC. People call it a bunch of different things, I call it AUC. But AUC stands for area under. Now, what it is essentially at different thresholds. So the history is that like these rock curves, they're called super operating characteristic curves. They were used back in World War I or II. Which was the one where they figured out radar? I think that was one, right? Yeah, okay. World War I, yeah. Back when they first figured out radar, they wanted to know how good the radar was at different thresholds. They would, you know, plot its true positive rate versus false positive rate at each threshold, and they would graph it on the surface, right? Now, if you take the area underneath this curve, wow, that's sorry, no. If you take the area underneath this curve, then what it does is it gives you a measure. I mean, it gives you a measure of how big your model is, right? Now, if you can see in the graph right there, a random classifier would have like a straight line that goes in the middle. And since this, I mean, I don't know how many of you are taking calculus and doing integral, but at the same time, it's also just easy. It's an area square with the area of 1 times 1, so it's 1. And you know, if it's just a diagonal line down the middle, the area is 1. Right? That is basically flip a coin and see what happens. If you have anything that the dot perfect classifier, again, you want something that goes up as much that point as possible. So you can see how you know, the blue classifier and the green classifier are like better than the random classifier, and that's because they've got a higher area under their curve. They've got a higher AUC. Right? AUC is nice in the way that it ranges in the same thing from like same area as accuracy, right? So like, you know, 50% accuracy is like half decent, and then like, you know, 90 is really good, stuff like that. So it ranges in the same way from like 0 to 1, but in that 0 to 1 interval. However, you know, it's a little harder to interpret. So as I said, it's better with unbalanced data. Also, yeah, so it's better with unbalanced data, and it's better for like ranking models, so like higher insights, because then you can measure the AUC, you know, your choices. And it's also visual because you get a graph. Now, I do not want to I don't want to understate that visual component enough, because, or, I don't want to gloss over visual components. Visual components are actually really nice for when you're measuring performance. Having something that lights up or looks nice and pretty is very important when you're presenting yourself. Maybe not like the scientific paper, I mean, even in scientific papers, okay? There's a reason that mathematicians come up with all kinds of crazy looking graphs. It's because if you have a nice looking graph, people like to look at what you're doing. That may sound like a funny joke, but Soham and I are working on a research project, and one of the things that we are doing is we had to include a nice graph of our results there. And the reason we have to include that nice graph is because, people can look at that and easily go, oh, funny color, what is that? Right? And we can explain it, we can be like, oh, I'm glad you're X, let's tell you what's going on. So that's the whole idea with that's the whole idea with visual components. It is any metric that you can get into some sort of graph or matrix or whatever that you can plot and show colors on and stuff. It sounds corny, but it can be very, very, very useful, especially if you're working in a place where you need to present binomials. Right? So, yeah. Now the comps for AUC, sorry. Yeah, sure.
So each classifier is only a point, right? So are we seeing like which block curve the point by?
No, each classifier isn't necessarily a point. This is what I was saying with this is what I was saying with like it can be hard to interpret as I was about to get into. They're basically each point of the graph is like I looked through the Wikipedia earlier. In fact, I still have it up right now, so I can check real quick. Because I was trying to understand it myself. All right, the ROC curve is created by plotting the true positive rate against the false positive rate at various threshold settings. So I don't know what they mean by threshold settings. I know that back in the day that probably meant like to turn a dial on a radio and do some changes. But like that's not something with machine learning models. So I can't necessarily tell you the specifics.
Yeah, I just asked because you would assume it only has one false positive rate and one true positive rate.
Yeah, I agree with you too, but then my issue is why don't we graph it as just two straight lines instead of looking for most of those are differential. So why is it smooth shit out of us, right? If it's just one point. So I don't honestly know. But yeah, I mean that's if you see it's in the con slide. It's semi-obtuse to explain thoroughly because you have to go into how that ROC curve is plotted. And yeah, I mean, I can't necessarily tell you all that stuff. What I can tell you is that you don't have to worry about it because Seth will never do it for you. So you can kind of just get the plot and pull one of the old, I don't know what this is, but I know that what I'm getting is good. So you can pull one of those. But in general, one of the bigger issues with ROC is that it's not necessarily designed for multi-class problem. So if you have a multi-class problem, you would have to plot multiple different ROC curves, and you have to consider an AUC for each class. I think some people do an average AUC for that, so if you have like 0 versus 1, 0 versus 2, and that stuff. But I mean, whatever. In general, it's just it's kind of a pain for multi-class problems, and it's used, but I don't know how often it is in my very limited research. So. But it's for binary problems, it is a very good method. Now, third one, my favorite one. You guys remember from last lecture, I showed you a thing called confusion matrix. This is a confusion matrix. It measures the performance of the model over all possible classes. So what you have here is, I'm not gonna start moving off that camera because that's gonna look weird. But yeah, you can see like on the x-axis, it has the actual label. On the y-axis, it has the predicted label. And essentially at each square of the matrix, so at each cell, it tells you how much or how many of a given number of examples. So if you have a given number of examples, how many of them from the actual label were predicted as that predicted. So for example, at 0, 0, you have like 382, right? That means 380, there were 382 examples which had, true label 0 that were given to predict that were assigned label 0 by default. And there were 105 examples of label 0 that had true label 0, that were given label 1 by default, down row, and so on and so forth. That's how it works. Now, ideally, you want your confusion matrix lit up on the diagram. That means that the highest number or the highest percentage of examples from each class was predicted correct, right? So at cell 0, 0, that means you predicted all of class 0 as class 0, predicted all of class 1 as class 1, so old and so full. And you want the other side to be a lot, you want all of the non-diagonal entries. Basically, you just want the same diagonal. Now, there is some variability in confusion matrices. If you, from looking up online, it's apparently not like a standard thing, which axis is predicted and which axis is actual. In general, when you're looking at a paper, read the axes. And for the purposes of anything you do, I will judge you heavily if you do it the wrong way. So the correct way is I'll show you in the slide. Do it that way, please. There are, again, a number of approaches. You can normalize it or not normalize it. If you don't normalize it, that means you just leave the wrong numbers. So you would plot it with just 382, 453, all of those numbers there. Normalizing it basically plots it as a percentage, so you see what percentage of label 0 is classified correctly, what percentage of label 1 classified correctly, so on and so forth. Again, please plot it as normalized. And the reason I say please plot it as normalized, this is something that like you can, again, I've written that you don't need to plot it normalized, some people don't. The reason I say plot it normalized is because it's better with proportions, right? So if I have something, but when you're plotting with image on MATLAB or MATLAB or something, right? If I'm plotting a matrix that has like 100 in the top left and like 0 and like 1s everywhere, right? That 100 square is going to be a lot brighter because according to the way that MATLAB will color things, it'll color it as like the highest number of colors, as close to white as we can, right? That's not necessarily good though, because say again, let's go back to the previous example where I have 99 of class 0 and 1 of class 1, right? And let's say that my model is like extremely good and it predicts everything correctly, right? Well, in that case, if I take the confusion matrix and I just do the raw numbers, so it would be, it would be a plot like this. I know it's a great story. Would plot something like this, right? If I do that, this, I just feed this into Matplotlib, this square is going to show up really bright, and the rest of these are going to be pitch black. And that's not ideal because, again, you want it to be lit up on the diagram, right? And if the model is doing well for every single one of these, then that means that you want like, that it's doing 100% accuracy for class 0. But I'm saying accuracy, like, it's predicting 100% of class 0 examples correctly. And it's also predicting 100% of the class 1 examples correctly, right? So when you normalize it, what you do is you essentially divide by the column sum. And so what they'll do is, okay, so say I have 99 and then divide that by 99 plus 0. That gives me like, 100%. And then I have, 1 divided by 1 plus 0. And so then when you give it, it'll actually, what you do when you normalize it, you'll feed it something that actually looks like this. Yeah, I'm not quite squares, but it'll be like 1.0, 0, 0. You'll plot a matrix like this, and this matrix is a lot easier because then Matplotlib will, it'll shade all of these in really brightly, and the rest of those will be pitch black. So you will be able to see exactly. You'll be able to, much more easily convey visually how well your model is working across. Now, confusion matrices do have cons, right? Now, pros, they're really good for class imbalance. So, I'll just show you in case we have one, right? If your model, let's say your model was, as I said previously, always predicting this first class, right? Well, then what would happen is that your confusion matrix would end up looking like this. We have this and we have that. And then you clearly see there's a problem, right? Because all the numbers aren't all on the diagram. They're all at the top for us, so you're on the 0. And also, again, visual design, as I said, that's pretty much, as you can see, lots of pretty colors right here. Real nice, real visually nice. Depending on the color bar, you can actually get ugly, so I advise you to the color bar, but you'll see all that. And also, you can derive metrics from them because, like, it shows you the proportion of each number of classes that's computed, right? So what we did last semester is we basically scored each team based on what we call the confusion matrix score, where we took the sum of the diagonal entries, right? Now, if you have like 5 classes, right, then when you normalize it, the ideal class chart will be a size 5 identity matrix, so it's kind of 1s all over the diagonal and 0s everywhere else. And so then if you take the sum of that diagonal matrix, take the sum of the diagonal entries, that should be at best, it should be fine, right? And whoever got closest to that number last semester, I think it was, I don't know, I don't remember how many classes we had, but it was like something like every two. And whoever got closest to like, 4 was the team that got whatever prize it was, right? So you can derive metrics from it if you want. You can technically derive metrics from other metrics as well, but confusion matrix kind of lends itself to that stuff. Furthermore, now for the cons, there is a lack of standardization. As I said, the axes can be different, like people can go one way or the other. But as I said, you need to, just whatever way you do it, just make sure you label everything so that way it's fun. Furthermore, it is reliant on picking good color gradients. And this is actually a sticking point of mine because there have been some research I've looked at where the color gradient was like massive. So like Matplotlib has a variety of different color gradients, right? Now I've seen some people plot confusion matrices with rainbow color gradients, right? Which means that like there's no real idea of like ascending like magnitude or color or like brightness or anything like that. It's like I guess we could all like visually just say like, okay, bright black is darker than purple, which is darker than orange, which is darker than black, right? I mean like that kind of, right? Whereas, like a light blue and a red aren't necessarily like darker or lighter than each other. Like for like just looking at it, it's kind of confusing without like staring at it for a bit to try to figure out what's going on. I've also seen some weird ones where it goes from like red to like white in the middle to like red, like blue or something. I mean, that one kind of works, but like why is it white? Like that makes no sense because having a white in the middle, I mean, you want the brightest color to be, at the top, not in the middle. Right? All of those color bars have different like applications for other different things, but for the sake of confusion matrix, pick a good color gradient that goes from dark to light, so that way you can actually see what the heck is going on and when this plot it makes sense. Otherwise, you kind of yeah. So as I said, today's lecture is going to be really quick. But first off, there are a lot of different matrices, different scores. There's like, Jet Hard Index, F1 score, like whatever. I've used all of the reason I've listed all of these is because I've specifically used every single one of them. That doesn't necessarily mean that, they're always going to be the best one for a certain task. In some cases, you want different types of, as I said, you want different types of measurements depending on what your task is. So ultimately, while it is kind of an unsatisfying conclusion, it is entirely up to you to design the most useful metric for you to decide your most useful metric for the task that you do. And now, I mean, look, it's up to you as far as figuring out if it's all within your domain. For the sake of this project, I don't necessarily know what sunrise planning is, but I'm going to tell you the basic confusion matrices if you like it or not. So, that's the idea in the end of it. But when you're working on this for real, it's all up to you. Like picking what sort of metric is the best to show off your model is your choice. And furthermore, you don't always want to restrict yourself to one, right? So, I mean, as we just saw, the 3 we looked at have different pros, right? Some of them will be better for certain tasks, some of them will be better for other ones, but you want to use a variety. So, for example, when I'm working on like binary classification, I had a paper recently on it was actually one of these. That was the one on no, it was one on diagnosing erythema, not erythema, that's the one just diabetic retinopathy. So basically when you're diabetic, blood flow is not great, right? And so what can happen is blood flow to your eyes can get a little puffed and as a result you can start to hallucination, that's called diabetic retinopathy, and you can figure it out from looking at retinal scans, but there weren't really like great models for, or there were great models, but like we attacked like trying to figure out like low training. Anyway, point aside, there were 2 classes, right? No diabetic retinopathy or diabetic retinopathy, or the binaries. And what we did was we didn't just use one of these methods, right? We reported the accuracy because we balanced our test set beforehand, right? We made sure that our test set had a balanced composition. Furthermore, we reported stuff like sensitivity, specificity, recall. I think we did do weight score, weight cap on that one as well. We also put confusion matrix for our model, and we put down the rest, right? So you can see that is like every bloody metric that I've listed on this slide. Which is my list on the slide, but point stands that like, we didn't just use one metric, we used a giant host of them. And the point is that like, if you're good with one metric, let's say, right? Well, maybe your model is good for that specific task based on that metric. But if you're good, if you're scoring well in all of the metrics, then that means that you made your model, right? It's basically, it's literally the exact same as just, when you're writing an essay, trying to find sources to back up what you're saying. Essentially, the metrics are just numbers that show that the model that you made is really good. And if you show that multiple times over in different ways, then you show you made it. So with that, I'm going to jump into the notebook. First, I'll pause while everyone pulls that up. Links in the Discord, by the way, for those who don't have it. It should be in the Discord. If it's not in the Discord, that's on me. Check. It is in fact in the Pioneers channel in the Discord. So yeah, it's the first link in the message. So click on that notebook. It'll give us like, was it 5:49? It'll give us until 5:51 to open it up. But in the meantime, does anyone have any questions? Have some? If that be an actual question? All right, we'll ask it later. I was actually going to talk about that. But yeah, all right. Nobody has any questions? I'm going to jump over the notebook quickly. Dude, so Google is a pain as always. Now, first things first, I will recommend, as I do with every notebook, make sure that you make your own personal copy of it. For those of you who do not know how to do that, go to File, go to Save a Copy in Drive, and then use that copy, right? Do not use this notebook, it's the one I'll be using, and if you're going through it as I'm going through it, it's going to make things. It's just going to start running out. Cool. So, with all that said, the goal of this notebook was to demonstrate how SK Learn works. So, for those of you who are those of you who don't know, SK Learn is just kind of a great library, but in terms of measuring performance metrics for like the obvious stuff and even some of the semi-non-obvious stuff, SK Learn is really good. It's the specifically sklearn.metrics is the package, and it has basically everything. I mean, it has basically everything that you guys need for package. So, with that said, we're just going to go through that quickly. So first things first, I'm going to be showing essentially how these metrics can look, and so this is going to be a practical example of how having biased training data can actually seriously affect the way that these metrics come out and why you need to use more than one. Good. So first things first, just going to run through this quickly. Don't worry about the code in it. It's simply just making the data look like a certain way that I want it to look. Don't worry. If you want to investigate, the code in it, have fun. I read it full man. But in the meantime, we'll just run through this. Google says that is a very security solved. So yeah, that is going to load, and then so first things first, this is going to plot the distribution of data. As I said last time, whenever you're doing any sort of data science thing, whatever your like target attribute is, look at the distribution of the data. So for those, so in this thing, okay. Just out of curiosity, because that thing kind of has annoyed me and now I'm going on a side rant. Does anybody actually use filter keys or Swift or sheet keys or anything? It's just like you hold shift. I'm pretty sure everyone's discovered when they play Minecraft. You held shift for long enough that it will just give a big pop-up. You don't want to do anything with filter keys. I don't know. Anyway, like when you hit shift for long enough, it's like, do you want to enable filter keys? It's like some typing setting, and it always does that. And it pisses me off every time because I don't think anyone's ever checked this.
It's an accessibility.
Okay, now I sound like an asshole. I promise I'm not ableist, but yeah, okay, whatever. Point stands, it's just annoying. But anyway, aside from that, so this should plot the distribution of the data, and as you can see here, these plots. As you can see here, the training set on the left, testing set on the right? Now, we can see, and this is engineered by me, so it's not like, it's not like out of 12, but basically I made it so that the test set is just normal, right? It's more or less equally balanced. And the training set, it tapers off. So you have, it's like as you go down, you got less and less of each class, right? Now, the idea is to show how bias data set. So I forgot to mention this, the NS data set, same one as last time, the same thing as last time we did to work on it, but in any case, right? So this is how this is how it's distributed across the 9 classes. Now, next up, we're going to train a model. For those of you from last lecture, you will remember this one you'll remember this one. It's a random forest with 100 decimeters and that's at the 28. Now, I looked at it last time, we were able to get an accuracy of 96 or 97%, a really big difference, right? And that was with like more or less balanced training set, more or less balanced test, right? But let's look how it works when we have a very uneven training set. So I'm just going to run through all of these. These are just prediction, getting in prediction. That. Oh, yeah. So while it runs, first function we're going to be looking at is metrics. It has a thing called classification report, right? Now, classification report is nice because you'll see it. So it shows you precision, the recall, on score, the support. Support is not like a metric. Support simply just shows you how many you have from each class. So there's 980 classes of class 0 in the test set, 1,135 class 1, so on and so forth. It also shows you a accuracy, and then I don't remember what either of these macro averages and data averages. But yeah, so you can see you have an accuracy of 0.85 or 85%, right? You guys running this on your own, you may have a different number. If you have a different number, don't worry about it, shouldn't it? Don't worry about 5% is right? Now, given that having 85%, as I noted last time, for NS 85% is bad because any half decent model should get 99%. But just like without like much knowledge of the problem, you can look at that and go, yeah, 85% is pretty good, right? Solving the right? That's not the worst thing in the world, right? We can work with that as well. Well, you do. But well, the only way we can figure out why we're wrong is if we plot the confusion, right? So we just saw accuracy is misleading. Let's plot confusion. Quick side tip before I run it. When you're working on a project, when you need to plot a confusion matrix, I do not care. I'm actually asking you, please just copy paste this entire cell for yourself and use this function because making your own confusion matrix, I mean, it's not hard to like make one. Yeah, I mean, it's like the whole it's the whole thing with machine learning in general, right? It's easy to make a model, it's hard to make a good model, unless you know it, right? Same way, it's easy to it's easy to make confusion matrix. You just use learn to help confusion matrix, but that's similar to confusion matrix or something like that. And you can define a confusion matrix, you can use skills.inshow to plot it and all of that stuff, right? But making a nice looking confusion matrix is a pain, and frankly, you guys can do that on your own, but if you don't want to be bothered, because not what was a pain, then just things like this. So anyway, we're gonna run the function and we already see a problem, right? Despite us having an accuracy of 85%, which some could consider to be, half decent. It's actually, the model's not really that great. So it works really well for classes 1 through 7, right? 7 starts to tail off a bit, but will it, right? Yeah, class 8, it really starts to break down. You can see, it's like 74%, only good there. And then like class 9, it really breaks down, right? And this sort of makes sense. It sort of aligns with the this distribution here, right? We only had 5. I mean, like numerically, we literally had like 5 examples of class 9, and like 8 was like under 1,000, and so on and so forth. So naturally, for those two, it's going to drop off a lot, right? And especially for class 9, doesn't even know what to do. It's like, is it predicting all of them as 4? Yeah, it's predicting all of them as 4, and none of them is 9. So naturally, that's a problem, right? So this just goes to show that, like, naturally, if you have a biased data set, it can cause problems that when you look at things like the accuracy score, the accuracy and all that stuff, looks like all these numbers. For reference, all these numbers should be from 0 to 1, and they're all like on the high side of 0 to 1, right? So they're all pretty good. But like the accuracy is like 85%, not the worst thing in the world, right? But the confusion matrix says that if you're saying you're trying to use this as an sort of real world example, I can give it the number 9, it's going to shift hands. So with that, I mean that's it for today. Remember, like sign up for the project and everything. But with that, I hope that just show that when you're working on biased data or just with real world data in general, you can't just use one performance metric to measure anything. You need to use a variety of them in order to understand what's fully understand what's going on. Yeah, I'll stick around for questions if anyone has any, but other than that, y'all are free to leave. So yeah, and please come to the next lecture so you can know more about that. I mean, sure, yeah, kind of. So I mean, I'll take you through this function quickly. This is just matplotlib stuff to make the figure and the thing to plot stuff on. It's matplotlib can. This function is what makes the computer matrix itself. This one makes it normalized. So as I said, it divides by the column sum. So this normalizes that. This gets rid of nans. Don't worry too much. It's just there's like a class that's actually there but isn't in the models that they set them. So it'll spit out like nans in that column. So they will don't put nans there, but zeros. This makes an annotation array. So the rest of this is just like fun, really. So this annotation array just makes it so that it has all the numbers and percentages here. So actually, I should mention that like once you have it normalized, you can just plot it like that and just look at the colors and see what happens. I just like looking at the numbers and stuff because it just makes it look fancier and also conveys the numbers a little better, right? So with that, you just makes it makes all these labels. This here, use a library called Seaborn. It has a function called heatmap that throw in all these options so it'll plot the confusion matrix. This is the annotation array, so how they annotate all the cells. I don't know what this format thing does, but sure, we'll go with it. C bar equals true means to plot this color bar here. CMap, this is the color map, so basically what colors you map each value to. You can see if I change this to like, I don't know what one is, especially. Okay, there are a couple here. Let's go with something that will look nasty so I can genuinely show what that one is. All right, we'll do that. Great. And vmin, I don't know what, and x equals x, that's just type out, make sure everything works out fine. These are the set things, change the sort of the y levels that the actually work out. And when you hit shift enter, this is what I was saying about having a bad color gradient, right? This is possible. Don't do this, like genuinely don't. This is unreadable as hell, right? But if I return it back. So I mean to answer your question, yeah, there are simpler ways. This is, I mean, I'd argue this is pretty simple because like there's just like 3 main parts, which is confusion matrix, or make confusion matrix, make some annotations, lots of things. But like you could feasibly just like get the confusion matrix and then just PLT back and show it. You could do all that. I say copy paste this function is makes things look nice and not even necessarily for you, but also for us who are doing your projects. That's a whole different ballgame. Also, I'm doing my age in that stuff, so I'm my code. Actually, I don't know that. But anyway, yeah, I mean, there are simpler ways. Now, you may notice also, I just put aside, I didn't include AUC in here. The reason is because, again, as I said, AUC is not great for multi-class and having multi-class problem. We have a binary problem, we could put AUC and like, again, look the rest of it and figure out how to specifically do all that, but I don't remember it. I'm not include it right now, so don't worry so much. But yeah, as I said, with that, I'll stick around for questions, but y'all are great. Thanks for coming in. See you next time. And also keep updated on the Discord if you did not sign up for the project, because I, we'll try to get it up.
That's where the
Yes, so it returns a number. that's with that matrix. Okay. Specifically, it returns it unnormalized, so the numbers would be like, 974 and then whatever, like, pick all the top numbers, and then you normalize it by, again, you divide it by the column sum, so that's, that sum on X equals 1, just says, take the column sums and then divide each entry by the sum of the column, by the sum of the column. In order, okay. That is next time.